Let's now consider the graph of the function sine of x again. Now, this function sine of x is symmetric, and it's symmetric about the origin. Right, so what does it mean for a function to be symmetric about the origin? Well, if I consider this graph and I rotate this graph about the origin by 180 degrees or pi, then after rotation, the resulting graph will be exactly the same as the graph of sine of x. Right, so if I rotate this graph about the origin by pi or 180 degrees, I will get exactly this graph back. And if that is the case, then the graph is symmetric about the origin. So let's consider some point on the graph. Let's say we have some point a comma b. Now if I rotate this point about the origin anticlockwise by pi, then I will reach this point. After rotation, I will have this point with the coordinates minus a, minus b. Right? And the endpoints, so the line segment will have a midpoint at the origin. So this is our origin with the coordinates 0, 0. And so we can see from these coordinates that, so when y is equal to b, from this function, we can see that sine b is equal to the sine of a. And from these coordinates, we can see that when y is equal to minus b, we have minus b is equal to the sine of minus a. So we end up with these equations, and we can combine these two equations together to see that we have sine of minus a to be equal to minus b, which will be equal to minus sine of a. Now, why is it minus sine of a? Well, if I just multiply this equation by both sides, on both sides by minus 1, we will just get minus b, which is equal to minus sine of a. So sine of minus a will be equal to minus sine of a. So I can write this as sine of minus x will be equal to minus sine of x. So now I have reached this equality. This will be also an example of a trigonometric identity. So this is a trigonometric identity. Right, and this holds for all values of x. Similarly, we can consider the graph of a cosine function. And we should know that the graph of a cosine function looks something like this. Right, this is pi, 2 pi, right, so this is the graph of the cosine of x, and the function cosine of x is symmetric about the y-axis. So this is symmetric about the y-axis. Right, and you can see this for yourself. If we reflect this portion of the graph along the y-axis, I will just get this portion. Right. So cosine of x will be symmetric about the y-axis. Now, if I consider the point on the graph a comma b, then the point minus a comma b will also be on the graph of a function that is symmetric about the y-axis. And from these coordinates, we can see that when y is equal to b, so b will be equal to the cosine of a, and from these coordinates, b will also be equal to the cosine of minus a. Right, in this case, x is minus a. In this case, x is a. Right, so we will have these two equations, and we can see from these two equations that the cosine of minus a is equal to the cosine of a. Right, you can also write this as the cosine of minus x is equal to the cosine of x. So now we have another equality, and this will also be a trigonometric function, and it is valid for all values of x. Right, and this function, so the cosine of x, this is an even function. Right, so if I have some function f, where f of minus x is equal to f of x, then in this case, f will be an even function. So since we know that the cosine of minus x is equal to the cosine of x, well, we can see that this is being satisfied. So this equation is being satisfied for the cosine of x. Right, so the cosine will be an even function, and even functions are symmetric about the y-axis. And before I showed this graph, we were considering the sine of x. Well, since we know that the sine of minus x will be equal to the minus sine of x, then for an odd function, if I have some function f such that f of minus x will be equal to minus f of x, then in this case, f will be an even function. Sorry, f will be an odd function. Right, so we can see here that sine of minus x is equal to minus sine of x. And so this equation is being satisfied. So therefore, the sine function will be an odd function. And odd functions are symmetric about the origin, meaning if I rotate the graph of an odd function by 180 degrees about the origin, then I will get the graph of that function back. Now I can quickly show this using a unit circle. If I consider a unit circle, if I rotate anticlockwise by some angle theta, and the corresponding terminal point of theta is some point P with the coordinates a comma b, and if I also rotate anticlockwise by some angle theta, so this angle should be minus theta, and the corresponding terminal point is Q with the coordinates a comma minus b, then so we know that the y coordinates correspond to the sine function, and the x coordinates correspond to the cosine function. So using this coordinate, we have a to be equal to the cosine of theta, right? And from this coordinate, we see that a is also equal to the cosine of minus theta. So from these equations, once again, we find out that cosine of minus theta is equal to the cosine of theta. And for the y coordinates, we have b is equal to the sine of theta. And from this, we have minus b is equal to the sine of minus theta. And once again, considering these two equations, we have sine of minus theta to be equal to minus sine of theta. And these are both trigonometric identities. All right, so now let's consider a tangent function. So let's say y is equal to the tangent of x. Right, and the first thing I want to do is I want to graph this function. But before I graph this function, it is better if I know the period of this function. Now we know that sine of x is equal to the sine of x plus 2 pi, and that is because the period of sine of x is 2 pi. And for the cosine of x, this is equal to the cosine of x plus 2 pi. And once again, the period of the cosine function is also 2 pi. Since both of these functions have a period of 2 pi, then the tangent may also have a period of 2 pi. So to show this, or to find out what the period of the tangent function is, let's consider the tangent of x plus 2 pi to be equal to the sine of x plus 2 pi divided by the cosine of x plus 2 pi. Right, and this should be equal to sine of x divided by the cosine of x, which is just the tangent of x. So now we can see that the tangent of x plus 2 pi is equal to the tangent of x. So at best, the period of the tangent function can be a maximum of 2 pi, but it cannot exceed 2 pi. But it can also be less than 2 pi. So in order to find out specifically what the period of the tangent function is, let's first remind ourselves what the tangent function actually is using a unit circle. So once again, if I have some angle theta, and this is my terminal point, then the slope of this line will be the tangent of theta, right? And that will be sine of theta by cosine of theta, right? So the tangent of theta will just be the slope of the line that is connecting the origin to the terminal point of theta. All right. When we start rotating from this point anti-clockwise, so when we start with theta is equal to 0, we see that our slope is just a straight horizontal line, and we know that the slope of this line will be 0. And as the slope starts to increase with increasing theta up to pi by 2, the value of our slope also starts to increase. And once we reach theta to be equal to pi by 2, we will end up with just a straight vertical line, and we know that a slope for the straight vertical line will be undefined, right? So when we consider theta to be less than pi by 2 but greater than 0, we will have a positive slope. So tangent of theta will be positive, right? But when we're considering theta to be greater than minus pi by 2 but less than 0, well, that in that case we will have a negative slope, right? So when we have angles that create these slopes, so we have a negative slope, and as we start to go to minus pi by 2, the slope starts to become more and more negative until we reach theta to be equal to minus pi by 2, where we have a straight vertical line which is also undefined. Right, so now in our unit circle, if I consider a straight point that is passing through the origin, that in this case, our straight line is intersecting the unit circle at 2 points. So 1 point here and 1 point here. So for some angle theta, we see that this point is going to be the terminal point for theta. And from this point, if I rotate all the way to this point, then this is just theta plus pi, right? So this point will be the terminal point of theta plus pi. And we can see that this slope of the line is the same for both of these terminal points, right? The slope of this line is going to be the same for both of these terminal points. So if the slope is m, if we consider our slope to be equal to m, then we can see that m is equal to the tangent of theta, but over here m is also equal to the tangent of theta plus pi. So we can see that the terminal point of these two angles that are differing by pi will have the same tangents, right? So from this we can determine that since the tangent of theta is equal to the tangent of theta plus pi, for all values of theta for which tangent of theta is defined, well, that in this case the period of the tangent is also pi. So the period of the tangent is pi. So from this we can try and graph y is equal to the tangent of x. And first thing we can do is we can just graph for a single period. So if we consider x to be less than pi by 2 but greater than minus pi by 2, so let's say this is pi by 2 and this is minus pi by 2. Right, so from our unit circle, so when we're considering the interval from, right, so when we're considering the interval from 0 to pi by 2, we know that our tangent will be positive, right? We will have a positive slope. So we will start from 0, and then we will have a graph that looks like this, that gets closer and closer to the line x is equal to pi by 2, but it never intersects the line of x is equal to pi by 2, because we know that when we have x is pi by 2, our tangent becomes undefined, right? So the line x is equal to pi by 2 is a vertical asymptote. So this is an asymptote. And that is because the graph of the tangent never intersects this line of x is equal to pi by 2. Right? It only gets closer and closer as x approaches pi by 2. Right? And similarly, when we're considering this portion from minus pi by 2 to 0, we see, or we've shown that from a unit circle, we will have a negative slope that gets more and more negative as theta gets closer and closer to minus pi by 2. So we will have the graph becoming negative and getting increasingly more and more negative. And it gets closer and closer to the line x is equal to minus pi by 2, but it never intersects this line. Right? So this will also be an asymptote of the graph. So now, since we know that the period of the tangent is pi, then if this is pi and this is 3 pi by 2, then what we can do is we can just, from minus pi by 2 to pi by 2, the graph that we have obtained will just be repeated for the next pi interval. Right, so for this pi interval, we will just have a graph that looks like this. Right, so the graph of this portion will just be repeated again and again. So we will have a graph that looks like this. So this is the graph of the tangent of x. Right, so from our graph of this function, right, this is the graph of the tangent of x. So we can see that if I rotate this graph about the origin by 180 degrees, I will also still get this graph back. I will get the exact same graph, which corresponds to the function, the tangent of x. So that means that the tangent of minus x should be equal to the sine of minus x, which is divided by the cosine of minus x. So once again, from our trigonometric identities, we know that this will be minus sine of x divided by the cosine of x, which will give us minus the tangent of x. Right, so we can see from here that the tangent of minus x will be equal to minus tangent of x. So we have satisfied this equation. And if this equation is satisfied, that means that our function is an odd function. So the tangent of x is an odd function, meaning it is symmetric about the origin. So if I rotate the graph of the tangent of x by 180 degrees about the origin, then I will just get the exact same graph back.